Hello dear students, in this lecture we will learn about F region, in particular F2 region, and we will try to see what is a Bradbury layer and what are the chemical processes associated with this particular layer in ionosphere. So, before we begin what exactly is this layer, we should understand, we should refresh our memory of how the neutral species vary with respect to height and how the incoming solar radiation is absorbed at different altitudes. So, we all know very well that the ionosphere is created, ionosphere is formed when the extreme ultraviolet radiation, X-rays originating from the sun are absorbed in the upper atmosphere, resulting in the formation of electrons and equal number of ions. This layer of Earth's atmosphere is referred to as the ionosphere. So, the ionosphere is categorized into 4 distinct layers D, E, F1 and F2. So, the ionosphere is categorized into D, E, F1 and F2 layers. Now, in our earlier discussions, we have clearly seen what are these 4 layers. Why do we need to call them as layers, or what is the distinction between these 4 layers? Why can't we call the entire ionosphere as just a single layer, right? We have discussed all of that, detailed photochemistry of each of these layers, and we also know how many layers generally persist during the night time. And there are specific cases when something called as an F3 layer also appears. This is not a daily phenomena. This appears because of various electrodynamical processes in the ionosphere. Generally speaking, the ionosphere is basically made up of 4 distinct layers, right? Now, what are we trying to understand in this lecture is quite simple. We have to see the existence of F2 layer. So, existence of F2 layer, or why F2 layer persists. So, generally we put the F2 peak, the peak of F2 as somewhere between 200 to 400 kilometers in altitude, and typical electron density associated with this F2 peak is the highest, actually is 10 to the power of 12 electrons per meter cube. So, the point is there are these 4 different layers. Each layer is marked by a turning point where the electron density slightly shifts in its slope with respect to the axis, right? Now, the most important thing, which actually I mentioned about this height and electron densities in the earlier lectures, you remember we see that electron density increases upwards as we start from the bottom D region. We are moving towards the higher altitudes, the electron density increases. It is quite easy to understand this increase because as you are moving up, the number of available photons is increasing with respect to height, right? So, the solar radiation that is coming inwards is being attenuated, is attenuating as it travels downwards, and at the same time the number density is, as you go up, is decreasing at an exponential way, exponential minus h by h, and the incoming radiation I is equals to I naught e to the power of minus mu x. So, there is an exponential decay from the surface and there is an exponential decay of intensity from the top of the atmosphere, right. So, you can expect that these 2 exponential decays to reach a balance somewhere and create a peak. Now, we have also seen the meaning of this peak, how this peak is a function of the angle of incidence and how this peak is a function of intensity and so many other variables, solar zenith angle, intensity and many other variables which decide the position of this peak with respect to the height. So, you have the geometric height on the y axis and the electron density on the x axis. Now, what I am trying to say is the electron density shows a distinct peak, assuming that it is where n sigma is equal to 1, or we can consider the entire radiation is effectively absorbed. Right. Now, this is a very standard or very simple picture. It is very easy for us to get convinced. Right. Now, in order to understand this peak of F2 layer, which is placed somewhere between 200 to 400, I am telling you a very broad range of altitudes, and the typical density is 10 to the power of 12 electrons per unit volume in meter cube. Right. Now, that means that somewhere at very large altitudes, you are hitting complete ionization or most highest form of ionization. Right. Now, you go back to this neutral density variation with respect to height. You know very well that the atmosphere, like 99.9% of the atmosphere, is existing below the first 50 kilometers of altitude. So, as you go up, the density of atmosphere becomes very, very small, and the mean free path becomes very, very large. So, despite the fact that there are many number of photons available for ionization, there are not many number of atoms or molecules to get ionized. Right. So, now you look at this picture. The dark line that you see is the ionospheric density with respect to height. Right. Now, before we go here, let us look at all the densities. For example, densities such as O2, oxygen density, argon, nitrogen, atomic oxygen, helium, all these densities, all of them are decreasing with respect to height. So, at a particular height, let's say at 200, this is generally referred as 250 or 300 kilometers, right? So, this one is the F2 peak that I am talking about. So, here most of the densities are low. So, we have to find out a reason that why maximum amount of ionization is happening at a particular height where the number of neutral species is very, very less. The answer could be very simple. If you say that, of course, there are the number of atoms or molecules available for ionization is less, but at the same time, given the intensity of incoming solar radiation, it will probably be enough that all of them get ionized and you get highest ionization or highest electron density at this height. But what is more interesting is when you look at the way electromagnetic radiation gets absorbed. If you see this figure, which we have seen earlier in our discussions many number of times, you see that this figure shows the absorption heights of electromagnetic radiation incoming from the sun. Okay. Now, you can take any point on the line and you draw an intercept onto the x-axis, you will get that particular wavelength. So, this is 50 nanometer wavelength. Okay. And you draw an intercept onto the y-axis, you get the height, which means 50 nanometer is absorbed effectively at 150. And at the same time, we also know which species is actually absorbing this. So, 50 nanometer, you can put it in ultraviolet part of the spectrum. So, what you see here is that you draw intercepts onto the x-axis and y-axis, you will be able to find what is the wavelength that we are talking about and what is the height at which this wavelength is absorbed, and at the same time, what is the chemical species which is actually absorbing this particular wavelength, right? You combine these two figures, what you will notice is that most of the energy is absorbed below 150 kilometers, below 150, or even let's say to a very broad estimate, you can say below 200 only maximum amount of absorption is happening, right? Now, what it means is that you are talking, if you translate this understanding into this figure, you will realize that not much is actually absorbed above 200 kilometers, right? When it is not absorbed, how are the electrons and ions created? And more importantly, how is it that maximum amount of electron density exists above a height, above an altitude where there is practically very little absorption, right? So, that means the production is not happening here, but still the electron density is the highest. Electron density is highest between 200 to 400 kilometers. Wherever F2 peak, wherever it is, electron density is happening. But if you translate that height into the absorption, electromagnetic absorption with respect to geometric altitude, you will realize that production is not efficient. So, you are talking about a particular height where there is no production, but then you are saying that at these heights we expect maximum amount of ionization. These two are quite contradictory in nature, right? You can situate the F2 peak anywhere here below this absorption line. It is very easy for us to believe that, of course, there is a lot of absorption, there is a lot of electromagnetic energy that is being absorbed by the gas species and resulting in the formation of ions, electron density, right? So, but here there is a small contradiction in which you are getting maximum amount of electron density at a height at which there is little absorption, right? So, what is the reason that we are experiencing something like this? If you go into more details, this is how the ionospheric structure looks like. So, this figure shows the variability of ionosphere with respect to height and with respect to solar maxima and minima. In both the cases, F2 region is the most dense plasma in the Earth's ionosphere, and F2 region also happens to be sitting at a place where there is not much production happening, because the absorption curve is not telling you that this is where the maximum amount of energy is absorbed. We know from the Chapman theory that wherever maximum amount of absorption is happening, that's when the n becomes equal to sigma inverse, or we can assume that ionization is happening at the highest magnitude, right? So, the confusion or the anomaly that we are trying to discuss is the F2 peak and production. What is production slash recombination? Okay. So, we are trying to understand why the peak electron density is found at an altitude where the production itself is less. Okay. Now, in order to understand, we will have to re-evaluate both the production mechanism as well as the loss mechanism. We will also need to see what is the role of diffusion in creating the maximum amount of electron density at a height where there is not much of ionization actually happening. This is the confusion that we are going to resolve. The layer of ionosphere is going to be called as the Bradbury layer, right? So, this is the peak F2 electron density, F2 peak, and the role of production slash recombination in situating the F2 peak at, let us say, 250 kilometers with an electron density of 10 to the power of 12 electrons per meter cube. Okay. Now, the most important factor which actually contributes to this anomaly is that incoming solar electromagnetic radiation, there is no spectral band, there is no spectral band which has maximum ionization above 180 kilometers altitude, right? Now, what does it mean? The answer simply lies in the fact that the height variation of recombination rate, the height variation of recombination rate. There are several processes by which electron density is effectively removed from the ionosphere. Some processes are very fast and some processes are very slow. And the primary reason why the F2 region persists during the night time is that the processes which are trying to remove the electron density from the ionosphere or F2 region, they have a typical time constant which exceeds the duration of the night itself. So, that means even the night is complete, the recombination is not yet complete, which means electron density is not completely removed, right? Now, the height variation of recombination rate. So, in order to resolve this F2 peak, its position in the atmosphere and its relevance with respect to the absorption above 180 kilometers, all of this can be simply resolved by saying that probably the production is small, of course, at these heights, but the recombination rate is very, very small. That means whatever that is being produced is not removed from the ionosphere by the means of chemical recombination, right? So, we are going to realize that with the help of simple equations, and then we will be in a better position to answer this anomaly. Okay. So, F2 region is basically an extension of F1 region, although the production is decreasing with respect to height. Why? Primarily there is one reason. Why? Because there are not enough number of takers. Okay. So, in these altitudes, the major ionic species is basically O plus is the major ionic species. Okay. Now, this O plus can be lost, or O plus upon recombination with the electrons can result in the formation of a neutral state. It follows a two-stage recombination process, what is called as a two-stage recombination. What is it? The two-stage recombination is step number 1 is when NO plus reacts with N2, giving NO plus plus N. Okay, let us call this as 1. Second step is this NO plus recombining with an electron, giving you N plus O. This is the dissociative recombination, right, in which a molecule upon recombination with electron dissociates into these two atoms. Fine. Let us call this as 2. What is this? This is the two-stage recombination process of O plus. Okay. Now, the first process, the speed or the pace with which this, or the rate at which this reaction proceeds, the rate will be proportional to a constant beta times O plus. Okay. Of course, it will obviously depend on the availability of O plus, right? And then the second process proceeds at a rate which is proportional to NO plus times electron density. Okay. Now, reaction number 2 controls the overall rate at low altitudes, generally at low altitudes. Reaction number 2. So, 2 is important, or controls at lower altitudes, and number 1 is in control, is the rate determining stage at higher altitudes, right. That means not at every altitude both of them are not equally important. So, at lower altitudes 2 is dominant, and at higher altitudes 1 is dominant. So, there must be a height where there is a transition between 1 and 2, right, or 2 and 1 if you are traveling from below to top. So, up to a certain point of time you will see that reaction number 2 is dominant and reaction number 1 becomes dominant after a point of time. So, this height at which this transition occurs is called as the transition height. So, this transition occurs at h is equals to ht. We can write this mathematically at h is equals to ht, beta times O plus at ht becomes equal to alpha times NO plus times electron density. So, beta and alpha are the coefficients basically, right. Or we can write it as beta at ht is alpha times Ne. So, where ht is the transition height, which is generally between 160 to 200 kilometers, where ht is the transition height. So, this is also, I mean, fitting the description because that's where we expected the transition to occur. Because after that, we know the F2 peak actually persists, right? And for the F2 peak to persist, this recombination O plus plus N2 is not a dissociative recombination, right? But the dissociative recombination with an electron is the one that you actually want, or is the one that is actually fast. So, this transition occurs at an altitude where this balance is maintained, and mathematically we can write it as a simple equation. In the absence of let us say F1 ledge, what will happen is that this transition height is going to be greater than the peak production height. Yeah. What will happen in the absence of the F1 ledge? What will happen? The transition height HT will be greater than the HM. What is HM? HM is the peak production height. Now, for reference, peak production height has no relevance for F2 peak. Okay. The total available electron density, which is the highest, has little to do with the rate at which electrons are produced. Rather, it has everything to do with the rate at which electrons are recombining and getting lost, or resulting in the formation of neutral state. Right. Now, to explain the formation of F2, we can consider the upper part of the ionosphere where recombination is beta type, and it is obvious, like this recombination denoted with a coefficient beta this is referred to as beta type. Okay. Now, in the upper part of the ionosphere, or in the upper part of the F2 peak, we can consider the ionosphere dominated by beta type recombination. And from this reaction itself, we know that beta obviously depends on the concentration of N2. How many number of N2 is present, that will decide the loss of state or the creation of NO plus, right? So, is actually a function of N2. Beta depends on N2. O plus is produced, right? O plus is produced. So, that is ion, right? Now, if O plus is produced, the reaction must be O plus plus H nu should have resulted in the formation of O plus plus electron, right? This is the production process. So, this will obviously depend on the availability of O, oxygen, right? So, production rate obviously depends, and right. So, this is before talking about the loss, production depends on O, but the recombination depends on N2. Okay. Now, at equilibrium, what will happen? The number of electrons at equilibrium condition, the number of electrons, electron density will be proportional to the rate of production, of course, and will be proportional to the recombination or loss. The number of free electrons will depend on the recombination in inverse way. It is quite natural. More recombination, less number of electrons, and less recombination, more number of electrons. So, effectively the total number of electrons at any instant will depend inversely on the recombination coefficient and depend directly on the production rate. Now, we have defined beta type recombination, which is given by equation number 1. This photochemical process, actually, this process is dominant above 200 kilometers, and below 200 kilometers process number 2 is dominant, where NO plus, which is a molecular ion, will be lost as and when there is an available electron. Right. Now, let us try to see. So, effectively the number of electrons can be written as proportional to Q by beta. Okay. Now, we have already understood that Q is production rate is proportional to the concentration of oxygen, because this is the process which decides the production, and the beta type recombination is going to be proportional to the number density of N2. You see this O plus, you are getting O plus by the means of Q, and you have, depending on the number of available N2 nitrogen molecules, this recombination O2, let us say there are 100 number of O plus ions and there are only 2 nitrogen molecules. Okay. So, what is deciding here? The 100 is not deciding factor. The deciding factor here becomes the two molecules of nitrogen, they can recombine with O plus and create this NO plus molecule. So, that means the population which is lowest will decide the chemical kinetics, and at the same time, if you have so many chemical processes competing with each other, the overall completion of the cycle will depend on the slowest process, not the fastest process. Right. So, if the slowest process is taking certain amount of time, that will decide the overall completion of that particular process. Right. Now, here we are looking at this equation because O plus is dependent on Q, N2 is depending on loss. So, maybe we could have written one more simple equation which is actually a genesis for this discussion. O plus H nu gives you O plus plus electron. Why are we specifically talking about only oxygen? You go back to this curve. You see here, if I remove all this, see here, this one right there is O plus. Because of the dissociation of oxygen molecule, availability of atomic oxygen at these heights is explained by the photodissociation of oxygen molecule. And that means O is available here. That's when it forms an ion. Right. Coming back, so we have these three processes. Let's say we call this as A. A is the process by which electron density is created. When we are still talking about the ionosphere. Process number 1 is a route by which O plus is lost and creating NO plus. And stage number 2 is basically that stage when this molecular ion is dissociatively recombining with an electron, resulting in the formation of a neutral species. Coming back, so the total available electron density will be written as ratio of oxygen versus nitrogen. You see how simple it is. The total available electron density at any given period of time will depend on how many number of oxygen atoms are present, and at the same time it depends on the nitrogen density inversely. If there are more N2 molecules, the number of electrons will be less. That means electrons are lost fast. And if there are less number of N2 molecules, the number of electrons will be more. If there are more number of electrons, you see a peak. If there are not, you see something opposite. Right. Ne is proportional to O by N2. Right. Now, let us extrapolate this discussion. So, Ne is the available electron density is proportional to oxygen density divided by the density of N2. So, at any given height, the number of oxygen atoms can be written with a simple expression exponential minus h by the scale height of oxygen. See, here I am writing the scale height of oxygen. I am not referring the scale height, simply the scale height, because we know after certain altitude where the mixing of the atmosphere is not enough, each molecule or each atom, each species behaves with its own scale height. Okay, you can call it as the equilibrium where mixing is not adequate to create a uniform mixture of gases. Okay, because the mean free paths at these altitudes will be very high. So, it is natural that each species will behave with its own scale height. Okay, right. So, now we can simplify this expression and write Ne. This is minus, so it goes above, it becomes plus. So, Ne, the effective electron density will be proportional to exponential minus h by scale height of oxygen plus h by scale height of nitrogen. Let us say if these two species have the same scale height, I mean we have a trivial solution, but it is not, because their molecular weights, are not same, masses are not same, right. So, which means that we have the number of electrons is varying with respect to height like this. It depends with a negative exponential decay on oxygen density and N2 density positive, right. Now, let us stop here. We will see what are the consequences of this relation and how with this relation we will be able to explain the F2 peak at 250 kilometers when there are practically no spectral bands which are being absorbed at these altitudes, right? Which means production has little significance in the total number of electrons that you see here. So, the electron density at any given height h will depend on the dynamical balance between the scale height of oxygen and scale height of nitrogen. Okay. We will continue this discussion and see how we can explain the F2 peak at 250 kilometers when there are practically no spectral bands which are being absorbed at these altitudes.